Okay, let's go ahead and get started. So, today's lecture, I want to start off with a warning. So this isn't meant to scare you, but what we're going to talk about today is very important. And it's probably also conceptually the most challenging lecture so far. Bean, come here. So all this is to say that just pay extra close attention today, and if you have questions, as always, feel free to stop me so that I can clarify things. So I'm going to start by recalling a couple of things about cosets. So basically what we're going to do today is see that in certain situations, the set of left cosets can be viewed as a group. Okay, so we're going to understand when that happens and also see what those groups look like. So let's just look at this example again. Oops. So we had been looking at the cosets of the group generated by 3 inside of Z mod 9. So let's just recall what these cosets were. So we had this one, which is equal to, for example, 0 plus the subgroup generated by 3. We had this coset, and this is equal to 1 plus subgroup generated by 3. You can also write this as 4 plus the subgroup generated by 3, or 7 plus the subgroup generated by 3. And then lastly, we had 2, 5, 8. Okay. So what we're going to look at today is how to see that these cosets form a group where the operation would look like, so let's say I have two cosets, A plus the subgroup generated by 3 and B plus the subgroup generated by 3. So this is the operation. We would just first add A and B, and then look at the coset corresponding to that element. Okay, so the cosets are going to form a group with this operation, and this will be true in general for specific subgroups H. So not all subgroups do this, but something called normal subgroups do. So some subgroups H of a group G do this, and today we'll see which ones. Okay, so let's recall a couple of facts about cosets as well, just so that we have them handy. So we have already proved a couple of facts. So we know that, so let's let H be a subgroup of a group G. Then we know that AH is equal to H if and only if A is an element of H. Okay, so how this gets used often is when we're manipulating algebraic expressions involving cosets. Whenever we see an element of the coset appearing next to the coset, we just absorb it into the coset. So that's how I think about this property, is like as an absorption property. Okay, another thing that we already proved is that AH is equal to BH, or the two cosets are disjoint. And then a last property that I don't think we proved in lecture, but I'll just prove it now, is that AH is equal to BH if and only if A inverse B is in the subgroup H. Okay, so let's prove this now. So if AH is equal to BH, then we have the following. So that would mean that AH times A inverse oh no, wait. Sorry, did we prove this one already? Did we prove this in lecture? No, we didn't. Okay, let's prove it now then. So if AH is equal to BH, we can multiply both sides by A inverse, and we'll have A inverse AH is equal to A inverse BH. And this means that H is equal to A inverse BH. And by the first property, this is true if and only if A inverse B is in H. So, okay, so we sort of went in one direction, but you can see that this works both ways. Okay, are there questions about that? Yeah.
Question actually about above. So you have like A plus the subset generated by 3 plus B plus the subset generated by 3. What operation is that middle plus? Like, are you because you're adding groups together?
Okay, yeah, so this is like, I'm defining what it means to add two cosets together.
You're defining that way.
Yeah, so we're defining this operation.
Oh, okay. I see.
Yeah. And I'll also note that, like, in order for this to make sense, and we'll prove this this lecture, that so there's multiple. This is one way to sort of represent one of these sets, right? I could have presented this to you as 1 plus 3, 4 plus 3, or 7 plus 3, right? I could have chosen multiple A's to represent this one coset. And so we're going to have to prove that this operation doesn't depend upon that choice in any way. So we'll have to prove that it's well defined. Okay. Other questions? All right, one more property of cosets that we need. And this one I don't think that we proved in class. Is that AH is equal to HA if and only if H is equal to AH A inverse. So why is this true? If we have that AH is equal to HA, then multiplying both sides by A inverse, I have the following. And this right-hand side is equal to H. So if I have AH equal to HA, then AHA inverse is equal to H. And you can also see that this goes in the other direction. So if I had AHA inverse equal to H, then again, by multiplying, say, both sides by A on the right, I would have AH A inverse A equal to HA, and this left-hand side is AH. Okay, are there questions about that? So subgroups satisfying. So if for all A in G, we have AH equal to HA, then H is a special subgroup. And this will turn out to be the class of subgroups for which the cosets form groups. So if for all A and G we have this property, then H is called a normal subgroup. And we'll see that this turns out to be a very important condition. And so we write this as H and then a triangle G. And let me just make a remark on what this means. So this does not mean that A little h equals H little a for all choices of A in G and H in H. Right? It means that for all A in G, there exists, or let's say for all A in G and for all H in H, there exists an H prime in H with AH equal to H prime A. So this condition is kind of like saying we can commute elements of G with elements of H up to, we might get punished by having to replace our H with a different H. So, so that is what this condition is saying. Are there questions about the definition? Okay, so let's see some examples of normal subgroups. So first of all, every subgroup of an abelian group is normal. Why? Because all of the elements already commute with each other. So we actually do have this version of the condition for abelian groups. And by similar reasoning, the center Z of G of a group G is normal in G. Okay, again, because what is the center? The center is all of those elements of G who commute with everybody. So clearly that means if I have an element in G, I can just commute it with an element of ZG. Okay. A not totally trivial example, so the alternating group A sub n inside of the symmetric group S sub n is also normal. Okay, so why is this? So we need to show that if I have any permutation sigma, the left coset of sigma on AN is equal to the right coset. And by a property from above, this is true if and only if A sub n is equal to sigma A sub n sigma inverse. And okay, so let's see why this would be true. So let's let sigma A sigma inverse be an element of A sub n. So that means that, be an element of sigma A sub n sigma inverse. So that means that A is an element of A sub n. So that means that A is an even permutation. So what can we say about the even or oddness of this thing? So this is even. Well, sigma and sigma inverse have the same parity. So if sigma and sigma inverse are both even, then this thing will be even overall. And if sigma is odd, then sigma inverse is also odd. And so again, this thing will be even overall. So since A is even, we have that this whole thing is even. So sigma A sigma inverse is an element of A sub n. Okay, are there questions? Okay, so then to complete the proof, we should we should prove this direction. Off of the top of my head, I don't see how to prove this inclusion. So if I have, let's say, an A in A sub n, how to see that A is also in, so we would need to show A is in sigma A sub n, sigma inverse. Does anyone see a quick proof for this? All right, I don't want to get too hung up on this, so this, we'll leave this as a question. And we'll move into the main theorem so as not to get hung up on this example. Okay, so here's the theorem. So let's let G be a group and H be a normal subgroup of G. Then the set, so the set is going to be the set of left cosets, AH, such that A is in G. And this set is going to be denoted by G mod H. So this set is a group under the operation AH times BH, so we have to know how to multiply two cosets. So this is going to be given by ABH, where this is the group operation. And this is called the quotient group, or factor group. Okay, is the statement clear? Other questions? Yeah. Yeah. We'll see why. It's basically like, I guess the intuition is like, it's like looking at what the elements of G are if you consider everything in H to be the same. So it's like if you collapsed H, then what is left behind? What is the structure that's left behind? And that will make more sense, like as you see more examples, why it's called that. Okay, so let's prove this. Okay, so the first thing that we need to do is to prove that the operation makes sense. So we need to prove that the operation is well defined. And what this means is there are like multiple ways to represent this same coset. So I need to show that it doesn't matter how I chose to represent this coset. So specifically what I mean by that is that we need to show that if AH is equal to some A prime H and BH is equal to B prime H, then, well, when I define my multiplication, it shouldn't matter if I multiplied the A and the B or the A prime and the B prime. So I need that ABH is equal to A prime B prime H. Right, because in my definition I chose to say what it meant to multiply these two elements in terms of A and B, but somehow that shouldn't matter on the particular choice of coset representative that I picked. So this is what I need to show. And just like as an aside, so you'll see this across mathematics that people say, when you make a definition, sometimes you need to show that something is well defined. And that always means you need to show that the choices that you made in the definition don't matter. Okay, so let's see why this is true. So let's assume that AH is equal to A prime H and BH is equal to B prime H. Then what this means is that there exists an H1 with A prime equal to AH1 and B prime equal to BH2. Okay, why is this? Because this is saying that since these two sets are equal, I could look at A times the identity, say, and this has to be an element of this set. Or rather, I'll do this in the other direction. So A prime times the identity is an element of this set, so it also has to be an element of this set. So there exists an H prime such that AH1 is equal to A prime. And same thing over here. For some H1 and H2 in H. Okay, then I can do the following. So let's see what A prime B prime H is. We want to show that this is equal to ABH. So let's expand this out in terms of the these two equations. So A prime is AH1 and B prime is BH2. And then we had H. Then I'm going to absorb the H2 into H. So I get AH1 BH. So this is by absorption. Okay, then since H is a normal subgroup, I can write AH1 HB. So this is because BH equals HB by an H is normal in G. Okay, and then I'll absorb again. So I get AHB. And then lastly, I'll unswitch B again. So I have A, B, H. And this is by H being normal in G. Okay, so that was what we wanted to show, that AB prime H was equal to ABH. So that shows that the operation was well defined. Okay, are there questions? Okay, so I'm going to now give you a few minutes to show that. So now it remains to prove the theorem. Of course, we need to show that the left cosets, G mod H, that this is a group with the operation that we gave. So AH, BH is equal to ABH. And it's been a while, so let's recall that this means that we need to show that there's an identity element. We need to show that there are inverses. And we also need to show associativity. So I'll give you a few minutes to think about this and discuss, and then we'll prove together why this is a group. Okay, so let's prove it. So what's the identity in G mod H? Yeah. Yeah, so the identity is just H. So why is this? Well, we can represent H by the identity in G times H. So then EH times, let's say, any AH, that is equal to EA times H, which is AH. Hey, no, don't do this. Okay, what about inverses? Yeah. Yeah, so if you had AH, then its inverse is going to be just A inverse H. So why is that? Well, if we had AH, A inverse H, this is A inverse H, which is then equal to H, which was our identity element. Okay, and then let's see why this is associative. So we're going to have like a big string of equalities. So let's have A, B, and C be elements of the group G. Then if I have AH times BH, and I do that multiplication followed by CH, okay, I need to show that this is the same thing as if I had first multiplied B, H, and CH, and then did AH afterwards. So let's see why that's true. Okay, so by the definition of multiplication, this is equal to ABH times CH. And again, by the definition of multiplication, this is then AB times CH. And then now I can use the associativity property in G to reassociate. So I have A, B, C, H. So this step is by associativity in the group G. Okay, and now I'm gonna like unmultiply. So this is AH times BCH. And then unmultiplying again, this is AH times BHCH. Okay, so associativity works. And that was the last thing that we needed to show that this is a group. So that completes the proof. Are there any questions about the proof? Yeah. So the question was, why don't we have to show that it's closed under the operation? I think maybe it's good to just observe that it is closed under the operation. So this AB is an element of the group, and so then this is a left coset. So this is going to be inside of G mod H. Yeah. Other questions? Okay, I have an improved proof of why AN is normal, so I'll just explain that quickly. So my original strategy, I don't know if this was going to pan out. So why is this? Well, there's two cosets. We have AN, which is the evens, and then any transposition, let's say tau, times AN, which is the odds. So each of these two things, whatever it is going to be equal to one of these two things. And if sigma is even, then this will be evens. And if sigma is odd, then this will be odds. So since there's only those two choices, that it will, and the parity doesn't depend on if I multiply sigma first or last. These two have to be equal. Okay, so that's a quick proof of why this is normal. Okay, so let's do an example. And maybe this example will start to justify calling factor groups G mod H. So so I guess we're going to take in this example G to be equal to the integers, and then H will be 4Z. So this is 0 plus or minus 4 plus or minus 8, and so on. Okay, so what is G mod H, which in this case is Z mod 4Z? I'm going to give you a few minutes to think about this and discuss, and then we can, we'll talk about it. Okay, so let's discuss this. Okay, so I claim that all of the cosets are given by 0 plus 4Z 1 plus 4z, oops, 2 plus 4z, and 3 plus 4z. So why is this? So this is a partition of the integers. So say I have some element A in the integers. Which coset does it belong to? I compute the number A mod 4, and it will live in the corresponding coset. So let me be more specific. What is that coset? So that is A mod 4 plus 4z. Does that make sense? So maybe we should do an example. Let's say I had the number 17. Okay, what is 17 mod 4? This is 1. So my claim is that 17 is an element of 1 plus 4z. The coset. Why is this? It's because 17 is equal to 1 plus 4 times 4. Okay, so do we believe that these 4 cosets are a partition of the integers? So this is all of the cosets? Yeah. Okay, so what group is this? We saw last time there's only 2 choices. It could either be Z4 or Z2 direct sum Z2. And which one is it? Yeah, it has to be Z4. And basically, like, why? By this reasoning, right? I'm already, by even just like saying which coset something belongs to, I'm already like computing with arithmetic mod 4. So this is true. Z mod 4z, the factor group is isomorphic to Z4. Okay, so let me just conclude with like a statement of just intuition about how I think about these things. So quotient groups is like, so let's say we're looking at G mod H. So this is like saying what does G look like if we consider elements of H to be the same. And what I mean by this is like, think back to when we were talking about equivalence relations. And partitions. So the cosets give me a partition of G. And what I'm saying is that like everything in one part of the partition is one element of my new group. So there is like some equivalence relation that's saying that elements in H are the same, or 2 elements are the same as each other if they differ by an element in H. So this is just like a statement of intuition, like how do you think about these things? And on Monday and next week, we'll get more examples of factor groups, and we'll see what you can learn about a group by looking at its factor groups. And I hope everyone has a nice weekend. Do you have a question?
Showing that and I can see why this is true if they're disjoint, and I kind of understand like the amount of elements in the intersection has to drive out what I want, but I can find a way of doing it that isn't like because it has to or like more close. I'm wondering if this might help, but I don't know.
Wait, so what is this?
It's like and it compares separate pictures.
You may need something that we haven't covered yet.
Okay.
Where did you find this?
It was in the review section, but it was
It's in like the 5 to 8?
Yeah.
Well, then you should be able to do it without anything after that.
Yeah. I mean, my like other thought was like maybe this is like kind of like a hint to do orbit stabilizer,
Oh.
but I don't see how that would be the case because like I don't know how to go.
I feel like that might be a good way to go. So you want something where so maybe this is viewed as the order of this,
Okay.
and then somehow one of these is the orbit of. Okay, so now we need like some mystery group acting on this.
Mm-hmm.
And then one of these should be viewed as the orbit with